Okay, good morning. We have really one goal today, and that's to prepare for the exam that's on Monday. Once your homework number 3 is due today, if you haven't brought it up yet, bring it up after class. I will send the homework solutions out and the solutions to the practice exams after we're done with class. Once we get past the exam, we're going to move on to Chapter 4. So there's the reading assignments for the first few, for at least for Wednesday of next week. So you can begin to look ahead to Chapter 4 once we get past the exam. So I thought the first thing I would do is to just open it up with any questions either about the practice exams or about the exam itself. Are there any of your questions before I just start going through the practice exams? Anything at all? No. Yes?
Could we expect the difficulty of questions to be similar to the practice exams, or maybe plus or minus? Or?
I tried to make the practice exams similar in difficulty as to the exam. Difficulty is always, in the eye of the beholder, but that's what I tried to do. I tried to make a variety of difficulty. So some of the problems are a little harder, some are a little easier. Tried to do that in the exam too. So in my opinion, yes, it's similar in difficulty. Anything else? Okay, remember we'll be starting 8 o'clock sharp. And all right. So let's go through with exam 1B. And first the short answers. So let's try to bang these out real quick. What's the diameter of a water molecule?
1 nanometer.
Okay, 1 nanometer is pretty close. I would say water molecule is a little bit larger than that, or a little bit smaller than that, about 0.3 nanometers. But with 0.3 nanometers, any answer from 0.06 to 1.5 nanometer would be correct. 1 nanometer is 10 angstroms, if you like using angstroms. Atoms tend to be an angstrom or 2 in size. So 1 nanometer would begin to get you up to a molecule that had quite a few atoms, maybe a dozen atoms or something in it, rather than just 3. And with 2 of them being hydrogen, it gets down to somewhat smaller. Okay, what's the diameter of the hemoglobin molecule?
6 nanometers.
What I have here on the answer sheet is 5, but it's pretty close to 6. Sometimes these molecules are not exactly spherical, so assigning a diameter is sort of a rough approximation. That's one of the reasons I give you the factor of 5 either way. But you could get by with anything from 1 nanometer to 25 nanometers, and you'd be in pretty good shape. But macromolecules, big proteins, tend to be on sort of the 10 nanometer spatial scales. Okay, now, probably the hardest one of the 4 short answers is an artery of diameter A contains blood flowing at a speed V. So here it is, diameter A, blood flowing at a speed V. At some point along the length, the artery splits into 2 smaller arteries, each with diameter A over 2. And what's the velocity in the smaller arteries? So you're trying to find, I'll call it U in the smaller arteries. Now, how would one go about doing this? Who's got a...
Set the flows equal to each other.
Okay, this is the one reason why this is on the practice exam and not in the real exam. You might get a little confused on whether this is a continuity equation problem or a Poisson-Fleta tube problem, but it's actually a continuity equation, like you said. The flow going down here has to equal the flow, no total flow going through the daughters. The parent flow is equal to the total flow of the daughters, just like when you divide Murray's law. And the flow is speed times diameter, or speed times area. Remember, that was one of the equations you had to know. So over here, you're going to have V, and the cross-sectional area you could write as pi, and this is diameter, so it would be a over 2 for the radius squared. And that's the total flow in the parent. The total flow in the daughter, well, first of all, there's two daughters. So you're going to have a factor of 2 because there's two daughters. And each one is going to have a flow u, the speed, times pi. And now the diameter is a over 2, so the radius is a over 4. So a over 4 squared. And now all we got to do is solve for u. The pi's cancel. This, v a squared over 4 equals 2u a squared over 16. And solving for u, we'll get a 2, we'll make that 8. 8 comes over here, you get a 2v equals u. U equals 2v. So the speed goes up in the daughters because their total area, even though there's two of them, it goes down because they're kind of small. So as the area goes down, the speed goes up, just like the rapids in the river, just like you take your garden hose and you put your thumb over the end, and the area at the end goes down, the speed of the water coming out goes up. So that one requires a little bit of calculation, not too bad. Questions on that one? Okay, here's a quickie. Units of specific heat capacity. What would be the units of specific heat capacity? It's going to be joules per Kelvin is heat capacity, and then specific heat capacity is per unit mass. So joules per Kelvin per kilogram would be the typical units you'd use. Yeah. There are other possible units, but they'd all be equivalent. Okay. Let's go on and look at the problems. And problem 5 is really it's a problem that's basically just looking at almost at units and simple calculations to get an idea of sort of what our metabolic needs are. So a hiker makes a vigorous 4-hour hike on a hot summer day. During the hike, her metabolic rate is 500 watts. So we said about 100 watts is normal resting metabolic rate. So she's moving pretty good. Hiker uses candy bars as her source of energy. Each bar contains 340 calories with a big C. So that's nutritional calories, which means 340 times 10 to the third little c calories. And I give you there, it's not at the top. I don't give you the definition of a calorie in the information at the top, but I do give it in the problem because I'm not expecting you to memorize what 1 calorie is, but it's 4.186 joules. Decimal point. Okay, how many bars must she eat to supply her energy needs? So, how do we go about getting this? Who wants to get me started here?
Find the total energy needed for the 4-hour hike.
Okay, let's find the total energy needed. You've got 500 watts, and sometimes it's useful just to remember watt is a joule per second. So to get the total energy, all we have to do is multiply by the time. And this is a 4-hour hike. But we don't like, we got seconds here and hours here. So we've got 60 minutes per hour, and we've got 60 seconds per minute. So we've got 500 times 4 times 60 times 60. 500 times 4 times 60 squared, which is 7.2 times 10 to the 6 joules. Now, we could convert all the bars that she's eating to joules, or we could convert these to calories. I just as soon convert this to calories at this point. So 1 calorie is 4.186 joules. So I just divide that by 4.186. So we're talking about 1.72 times 10 to the 6 calories is what this person needs. Or in other words, 1.72 times 10 to the 3 big calories, or 1,720 big calories. Well, we know that the typical person eats around a couple thousand calories, so this hike is going to take up quite a bit of, that's why she's eating as she goes. It takes quite a bit of calories. So, each bar has what? Contains 340. So all we got to do is divide 1720 divided by 340, and we get an answer that is 5.06 bars. And if you want to, you can figure she probably didn't bring fractional little pieces of bars, so we can just round this off and say five of those energy bars will get her through the hike, sort of break even. Not going to gain weight, not going to lose weight, but it's going to supply the metabolic needs. So, just gives you an idea of what sort of intake we need to when we exercise. Okay. So you need to know the different units, be able to convert between them. You don't have to actually memorize the conversion factors. You need to know how to use them. Okay, during the hike, at what rate must she breathe in breaths per minute in order to supply her body with sufficient oxygen? Well, there's a bunch of assumptions here. Assume the volume of each breath is 2 liters. So, 2 liters for each breath. And she's breathing deeply. The air is 20% oxygen. So that's just a standard number for our air. It's 80% nitrogen, it's 20% oxygen. And there's a tiny little bit of other stuff, but it's mainly that. And the lung extracts 20% of the oxygen in each breath. So when you breathe in, your body doesn't extract every bit of oxygen that's in the air. It only gets 20%, so that's another 20%. And when the body metabolizes carbohydrates with 1 liter of oxygen, so 1 liter absorbed by the body, you get 20 kilojoules. Kilojoules of energy per 1 liter of O2. So this is another case now where we're just going to have to work out the calculate. So we're going to, during the hike, at what rate must she breathe? So let's say we're going to call that the rate. I'm going to have to come up here. The rate, which is the rate in, really we're looking for breaths per minute. So this is an example where units are your friend, because if you just make the units work out, you're practically going to get the right answer. So we want to total we got to know how many total breaths. Well, we can work out, first of all, let's see, how did I do this? I said energy per breath is equal to, well, you got 2 liters in each breath, and each breath will give you 20% oxygen, and you only get 20% of that out. And you get, let's see, you're going to get 20 kilojoules. So let's make that 20 times 10 to the third joules per liter. And so we just do that calculation out. And what we'll get when you do that calculation is you get that you're getting 1600 joules for each breath. That's how much energy you can convert, assuming you're rate limited by the amount of oxygen. If you have that much oxygen, you can convert and get that many joules from metabolism from the oxygen that you're feeding. Okay, now what do we want to know? We want to know the rate of breathing. Well, we figured out the total number of joules for the whole trip. So that means the number of breaths is going to be, let's see, 1.72 times 10 to the 6 joules. So I did that in calories. We never did get the joule. Here it is, 7.2. This would be in joules. 7.2 joules divided by 1.6 times 10 to the 3 joules per breath. And that's going to give us something around 3,000. When I did the calculation, I got a little more than that, 4,500. Total number of breaths. So now what do? We're looking for the breathing rate.
Divide by the time.
Just divide by the time, which is this number. If we want ultimately breaths per minute, you just divide by the time in minutes. So you take 4,500 and you divide by 4 to get hours and divide by 60. You end up getting 18.75, or essentially 19 breaths per minute. And it's useful to think about that for a second. That's pretty close to 20. 20 would be 1 breath every 3 seconds. It's a little faster than what we normally breathe when we're just sitting around, but she's out doing this strenuous hike.
They're like deep breaths.
Yeah, and it's deep breaths. So she's chugging along. I mean, this hike is not just a leisurely stroll, but that's a reasonable number. If we had mixed up a decimal point and gotten 190 or gotten 1.9, you ought to immediately say to yourself, something's wrong here. So think about your answers. Think, once you calculate, think, and remember, just like on the homework, if you calculate something, and even though it's a fairly innocent error, like you screwed up a 10 to the third somewhere and made it 10 to the sixth, and it seems like it was a small thing, but if your answer comes out ridiculous, I'm probably going to take off more points than if you got it, say you got it wrong because you messed up a factor of 2 somewhere, so your answer seemed kind of reasonable. You're going to get penalized more if your answer is sort of way off. So think about your result and ask yourself, does this seem reasonable? I try to make the problems so I don't get some unreasonable, unrealistic number coming out. Okay, one more problem about this hike. The only mechanism by which the hiker can dissipate heat is by sweating. Well, that's sort of an assumption. But let's assume that all the other mechanisms are sort of negligible compared to sweating. How much sweat in liters is required on the 4-hour hike in order to maintain the body temperature? And I give you that the evaporation of 1 kilogram of water is 2259 kilojoules, so times 10 to the 3 joules per kilogram of water. Okay, well immediately you can either calculate this out or you just remember. A liter is a kilogram when it comes to water. That's just a nice rule of thumb to remember. If you did it from the density if you wanted to. So if this person is doing this many joules per liter, we know the total number of joules. That was this. This is the joules per liter. So 7.2 times 10 to the 6 joules divided by, let's just write this as 2.259 times 10 to the 6. Another way of writing that, joules per liter. And that's going to come in the 10 to the 6's cancel out. And you get 7.2 over that. Let's just calculate it. 7.2 divided by 2.259 is going to give you 3.2 basically. That's what I got, about 3.2 liters. And again, that's reasonable. If you go on a hike like this, you probably bring along a water bottle, and it's probably, you probably need more than that for that long hike, but not a whole lot. That's a liter or maybe something a little less. So you got a pretty big water bottle, and maybe you stop and refill it halfway because it's a 4-hour hike in the hot weather. So again, it's a reasonable result. Yeah?
Did they tell us it's 37 degrees Celsius just so it's the same as air? It just seems like they didn't even include it.
It's not really needed. The only thing that really one thing about 37 degrees Celsius, if it's 37 degrees outside, it makes the whole assumption that the only cooling mechanism is sweating more reasonable. Because if your body's at 37, that's our body temperature, and the outside's at 37, then convection and conduction and radiation are all zeroed out. So that's really, it's to sort of justify that assumption of sweating. But you're right in that as far as a number, it was never used in the problem. So that it is fair game to throw in extra information. I will sometimes do that, not just to try to trick people, but one of your things you're hopefully learning is how to pick out the information you need to solve a particular problem. Yeah.
For the exam, would you prefer us to round the numbers instead of both sides, like 13 bucks versus 18?
For that case, the case you just showed me, 19 versus 18.7 or 7.5, I don't care. If you give me 18.756325341, I'll probably write a little obnoxious note, but I still won't take off. If you round it off to 20, and I did the whole problem right, I would probably still give you credit. I certainly would in this case because a lot of the data is only known to that level. But I would suggest not doing drastic rounding. I would suggest using the proper number of significant figures, or maybe one or two extra if you want. Just don't go overboard. But don't worry, it's not going to be graded on significant figures. Units, on the other hand, if you tell me 3.2, and I'm not sure whether you mean liters or cups or ounces, then I probably might not take it off in the homework, but this whole problem is each worth 25 points. You might lose a point. So be a little more careful with the units. If it's obvious from the problem what the units are, I'll be a little more lenient. But sometimes, for instance, with problems with pressure, where it's not exactly obvious what pressure units you mean, I'm going to probably take off a little bit if you don't give me the right unit. Okay, well, let's do another one. So I'll erase all of this. And now the next problem is really dealing with scaling, and it's a combination of a problem on scaling and a problem using log graph paper. So it gives you a little table, and I'm not going to reproduce the whole table here. Hopefully you have it there. And you're assuming a power relationship between the diffusion constant, d, and you write the power and the radius of some molecule, A. So we're going to write that as CA to the N. This is our usual scaling relationship, or what's called an allometric relationship, a scaling law. So you might say diffusion constant. We haven't talked about that yet. It's in chapter 4. But in this case, it's really a problem about scaling. You never have to know what the diffusion constant is. You just know you have some data, and you know this is the relationship. And you're trying to find C, and you're trying to find N, given a table of different diffusion constants and radii. So the question is, this question has you finding these, and also a plot. You're not required to plot the data, but it's useful to do it. So I'm going to start with plotting the data, just so we're all on board with that. Log paper. This is A in nanometers. And then the other axis is 10, 100, 1,000, 10,000. And this is diffusion constant. And for what it's worth, microns squared per second. And now that I see it, the squared, little 2 on the squared is really small on the exam. Sorry about that, but it is microns squared per second. Okay, let us plot the data. So you should get kind of comfortable doing this. Water has a radius of 0.13. So 0.1 is 3 is going to be between 0.1 and 1. It's going to be closer, remember, to 0.1. Remember, 0.2 would be about a third of the way over, and 0.5 would be about there. So 0.13 is somewhere around here. And 1615. 1615, that's going to be again, that's going to be 2,000. 1615 is about here. That data point right there. Next data point is going to be sucrose, 0.48. So that's about halfway over. And 438. So this would be about 5. So 438 somewhere around here. Inulin, a protein, 1.3. So that goes above 1. And 162. I'll say that's about here. Hemoglobin, 3. 3 is about halfway between 1 and 10 on the log scale. So 3 would be about here, and 70, that's way up here. Remember, 50 is about 2/3 of the way up, so 70 is going to be way up here somewhere. And catalase, a big protein, 5. So that's going to be maybe 2/3 of the way up, and 42, over halfway. And this is not the greatest plot in the world, but it is more or less a straight line. It's useful to verify that it's a straight line because otherwise this scaling relationship doesn't really hold. In this problem, I didn't ask you to plot it, so I probably couldn't require it, but I could ask you to plot it. Okay, so how are we going to find C and N? We've got a couple of ways to get N. One thing is if the graph paper has the same size tick mark from here to here as there, so if each decade is a given length, you could literally take out your ruler and measure the slope of this line and get N. So that's worth doing as a check. But if you don't want to do things just analog, we can take two cases. 1650 15, that's the case for water, equals CA, which is 0.13 to the N. And you take another point. I'm not going to put a whole lot of noise in this data, so you can really take any 2 points. But in general, it's nice to take 2 points that are widely separated. So we'll take the biggest one, which is 42 for catalase, is C 5.0 to the N. So what do you do at this point? If you want to solve for C and N, what would be your... Let's divide them. I'm going to kind of do it the sloppy way. I'll just divide them like that. 1615 divided by 42. I don't be able to do that in my head, but I'm going to be lazy. 38.4 equals, and here the reason why it works so well is the C's cancel. And so now you get, and this over to the N over this to the N really gives you 0.13 over 5 to the N, which is 0.13 divided by 5, 0.026 to the N. Now what do you do at this point? This is, sometimes I kind of gloss over this, but I want to solve for N. How would you solve for N at this point? Take the log of both sides. Because if you take the log, it doesn't really matter whether it's natural log or log base 10, as long as you do the same in both cases. Because the log of something to the N is equal to N log 0.026. So in other words, log of A to the B is equal to B log A. That's the relationship I use. That brought the N down. So now it's just a matter of dividing 38.4 log divided by 0.026 log. And you get N is equal to, I'm getting -1, which makes sense. That looks like it's about a slope of -1 coming down. So, minus sign in the slope means as A gets bigger, D gets smaller, which is exactly what you want. So we got it. Oh, one thing, when you get to this point, don't think that you can just take log of 38.4 divided by 0.026. that is not equal to log of 38.4 divided by log of 0.026. You need to know the rules of logarithms. You have to take the logs of each. This is what you got to do. And how do you get C? Yeah.
Take the case, plug in the one that we have, and solve for C.
Okay, you can really take either of these two. 16, 15 equals C. And now n of minus 1 really means you're dividing by 0.13. That's the same as 0.13 to the minus 1. So you really just take 16, 13 times 0.13, and you end up getting essentially 21. No. 210. So that means that your relationship is D is equal to 210 A to the minus 1. Or in other words, 210 over A. Just make sure that's the same as what I got here. Yes. Now, it took us a lot of effort to get that. What you want to do is you want to go back to your little table and stick in several of the points and make sure it actually works. So that way you know whether you made a mistake somewhere or not. If you can stick in various values of A and get the same value of D as in the table, you know you did something right. Last part of the question is what would you expect D to be for ribonuclease, which is A is equal to 1.9 nanometers. Okay. Well, how would we do this?
Plug it into our equation.
You can just plug it into your equation, stick in 210 divided by 1.9, which is pretty close to 2, which means you're going to be getting around 100. And if you did it a little more accurately, you'd find it's 111 microns squared per second. So that's one way to do it. The other way is to come over here to your graph, 1.9, and if you're pretty skilled in the plots, you could go up, then you could go over, and you end up getting something that's about 100, maybe a little more. It's always useful to check it that way, just so you know that you haven't made some gross mistake. If you slip the decimal point and you gave me 11, you'll find it right away when you do that check.
So if we just use the graph, how much leeway are we allowed to guess the ribonuclease?
If you make it clear that you're doing it from the graph and you got within, say, 10% of the right answer, I would probably give you full credit. Maybe take 1 point off, but probably not. But if you just wrote down an answer without any indication of how you got it, and you were that far off, it'd get a little more dicey. So it depends. But if you give me a pretty close answer, 10%, because you used the graphical method, you would get by far most of the credit. It's even better to use it both ways so you can do an internal check. Okay. Let's keep going unless there's other questions about this one. If you want to be comfortable with log paper and semi-log paper for that matter. Seven, estimate the Reynolds number for blood flow in a capillary. Assume the vessel has a diameter of 8 microns and a length of 1 millimeter, and there's a drop in the blood pressure of 20 millimeters Hg from one end of the capillary to the other. I give you an equation for the velocity distribution in the vessel. So that's going to be V is equal to 1 over 4. Again, I sometimes use mu, but 8 is the expression for viscosity for the book. R squared minus little r squared. Okay. We want to calculate the Reynolds number. First of all, what is the Reynolds number? What's the equation that gives you the Reynolds number?
L will be rho over the viscosity.
Okay, so rho LV over viscosity. So Again, one of the equations that you're supposed to memorize. Density, viscosity, some typical distance, some typical speed. So what we have to do is we have to pick out what the values are for these parameters. This is blood, which is pretty close to just water. It's got some red blood cells in it. So what would be our density for blood?
1,000.
Let's use the same as water, 1,000. I will not work out all the units, but if you do, they should all. Let's go ahead and put the units in because it may be important here. That's kilograms per meters cubed. Okay, the length, typical length. Now this, yes.
I mean, if we knew that the density of blood was a little bit higher than the density of water, could we just use that?
If you use, say, 1,100 because you thought it was a little denser, the thing about the Reynolds number is it's not meant to be exact. So I would probably give you full credit if you used, especially if you told me why. So I would say if you're going to choose some number that's not absolutely obvious, you should at least state what you're assuming. And if you do that, you should be in good shape. You might even be more accurate than we who used 1,000. You have to pick a typical length for this problem. Now, what's going to be the typical length? That's one reason why this is on the practice exam, not the real exam, is because I gave you two lengths. And it's not absolutely obvious which of these to use, or use, let's see, that was the diameter. You should use the diameter, should you divide it by 2 and use the radius, or should you use the length? Now, actually, I wouldn't use the length. The length is not what's really scaling this problem. It's not what's causing the pressure distribution and causing the speed. So again, I probably wouldn't put something this ambiguous on the exam, but I would use either the diameter or the radius. And in my calculations here, I used the radius, but if you use the diameter, Reynolds number is something that you can use either way. It'd be useful if you tell me what you use, but I'd give you full credit for either of those. So what do you put in for the radius, say?
4 times 10 to the 36.
4 times 10 to what I wanted to get is the times 10 to the minus 6. The one thing you have to use is you have to use all consistent units. If you're gonna be using the standard SI units, which is what I would recommend, you don't want to put in 4, because then your microns isn't going to cancel the units out. You're going to put in your 4, and I chose to use radius and not diameter here, so that's why it's 4 instead of 8. 4 times 10 to the minus 6. So you ask me during the exam, I've forgotten what a micron is, how many compared to a millimeter and a meter. I'm probably not going to tell you. You got to know at least those standard prefixes. Okay, now viscosity. What would you use for the viscosity?
That of water.
That of water is what I would use, which if you look up in this useful information, has both the density and the viscosity of water, 0.001. And the units are all, well, units are what they are. I'm not going to worry too much about the units. Again, if you thought, well, blood's actually a little more viscous than water, and you put in, say, 3.003 instead of 0.001, no problem. In fact, you're probably even more accurate. Now, the speed. The speed is the last thing we need. And we're not given that, so we're going to have to calculate the speed. How would you calculate the speed in this case?
Use their equation.
Use this standard equation. And you don't know exactly where to calculate the speed. If you calculate the speed right next to the vessel wall, you're going to get 0, so that's not a good idea because that's no slip boundary condition. Let's try it at r equals 0, so that term goes away. So this becomes 1 over 4 eta. Notice that your value for the viscosity is actually going to end up canceling out here, so it doesn't really matter what value you use. Times the PDX r squared. So 1 over 4, and here's times 0.001 for the viscosity. R squared is the radius squared, which we said was 4 times 10 to the minus 6. We're going to have to square it. Then we got to get dp dx. Well, I gave you the length. Here's where you need to have the length. That's the dx. The dx is the 1 millimeter, 10 to the minus 3. Now the dp, you're going to be tempted to put in 20, but you got to have things in pascals. If you're doing calculations where the units are important and you want to use SI units, you've got to convert this to pascals. Fortunately, some useful information. 133 pascals is 1 millimeter of mercury, so 20 millimeters Hg times 130, I said 30 pascals. I had 133. There is 1 millimeter Hg. So you can calculate that to be 20 times 133. 2660 pascals. 2660. Let's go ahead and calculate now what the speed is. 4e to the 6 negative and square it times 2660 divided by 4 divided by 0.00. Whoops. That's 4e to the 6 negative squared times 2660 divided by 4 divided by 0.001 divided by 1 to the third negative, and you get a speed of 0.011 meters per second. Let me just double check. I got 0.0106, so essentially the same. You calculate that all out, and it comes out to be 0.0424. And what are the units of the Reynolds number? No units, it's dimensionless. That's the beauty of the thing. You can calculate this in English units using feet and feet per second and pounds per square inch, and then it all work out and you get the same result in the end because it's a dimensionless number. And the fact that this is less than 1, what does that really mean about the physics? What can we conclude about flow in a capillary? It's going to be lower than 1, so it's low Reynolds number. Remember what the Reynolds number means? What does that tell you?
The range between convection and
Convection and viscosity.
Yeah.
Which one's dominant?
in this example, it's viscosity.
Viscosity is dominant. So this is a case where the viscous forces are really dominant, and that means the convection or the MA term in F equals MA are kind of negligible. And that means you don't expect things like turbulence and eddies in the flow. Those are things that happen with high Reynolds number. You expect a very streamlined, viscous flow in the capillary. Okay. Then there's an essay question. And this essay question is kind of a long-winded thing. I give you a little story. Sometimes I can't help myself. I give you little stories and pictures. This is about Caisson's disease, building the Eads Bridge in St. Louis. And what I give for the solution, this is the essay question, is a little bit, 1, 2, 3, 4, 5. I'll just read it to you. Caisson's disease is the bends. When breathing air at high pressure, nitrogen is dissolved in the blood. Upon rapid decompression, the nitrogen bubbles out of the blood, blocking blood flow in small vessels. To avoid the problem, the decompression must happen slowly. In this case, the decompression in the air lock must occur over a long time, say half an hour, so the nitrogen can come out of the blood without sudden formation of bubbles. Doesn't have to be a whole page story. Should be a few well-crafted sentences to cover all the major points. I would get you the 5 points. that is exam 1B. We can pause here for a second before we start on the final one, and let me ask, are there, again, any general questions you all have about the exam? I want you to have plenty of chances to ask them. Okay, well, let's kind of go through rapid fire here. Length of the E. coli bacterium. What's the length of the E. coli bacterium?
2 microns.
Oh, you
Oh,
said
sorry.
it's
Oh,
okay.
I
2 microns. Yeah, that's basically right on the button. 2 microns is a length of a bacterium. Diameter of a red blood cell. Oh,
8 nanometers. It's small. They're
That's neither as well. So what's even that?
I don't know, 8 microns.
8 microns is the answer. Yeah, so these are all or nothing. So 8 nanometers would have sunk you. But 8 microns is the typical size for a red blood cell. Do bacteria swim in water at high Reynolds number or low Reynolds number? Low. Remember, there's a factor of size, there's a factor of speed, and those two dominate for really small objects. So small things like bacteria swim around at really low Reynolds number. Okay, explain in one sentence. So this is kind of a mini essay. Explain in one sentence the no-slip boundary condition. So, by the way, what's the no-slip boundary condition?
The fluid, the velocity of the fluid at the boundary has the same velocity as the boundary of the fluid.
That's right. It says there's no relative velocity between the fluid and the boundary. So that's why in our blood vessels, right at the boundary, the velocity goes to 0. Okay, so those are the short answers. And I recommend you do it just like that. Bang, 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 get them done. Okay. Problem 5. Sweating is a mode of heat loss for the body. Even when no perspiration is evident, sweating from the skin and exhaled water vapor are on the order of 0.6 kilograms per day. So we do lose a little bit of water every day. What volume of water is lost per day? Well, that's an easy one. Who can tell me how much water is lost per day?
0.6 liters.
Yeah, you don't even have to think about it if you remember just a liter is a kilogram. That unit conversion is not given in the information, but it's implied because I give you what the density of water is and what a liter is. So it's 0.6 liters per day. What's the rate of heat loss in watts? Useful fact, evaporation of water is usually 2.5 times 10 to the 6 joules per kilogram. So I won't leave you hanging having to know that. But if you have that number, then what is the rate of heat loss in watts? Well, we know it's 0.6 kilograms per day. And we know that a kilogram is going to give us 2.5 times 10 to the 6 joules per kilogram. So the kilograms are going to cancel. So that gives us joules per day. But we don't really want per day. We would want it to get seconds to get watts. So 24 hours per day times 60 minutes per hour times 60 seconds per minute. And that will get us to, when you do that calculation, let's see, it's going to be a big number. 0.6 times 2.5 times 10 to the 6 times 24 times 60 times 60.
Should you divide by that?
I know it's why it's so funny. You're right. You want 1 day is equal to this many seconds. So I really want to divide by that. That way the days will cancel. It's oftentimes useful to go through the units and make sure what's canceling. You catch mistakes like that. Times 2.5 e to the 6 divided by 24 divided by 60 squared. It gives you 17.4 joules per second, which is a watt. 17.4 watts. So what that means is that you're probably not getting rid of all your heat. Your typical resting metabolic heat's about 100 watts. And a lot of it's going to go by radiation or convection. But even when it doesn't seem like you're sweating much, you will lose maybe about 17% through evaporation, just because that's the way it is. Okay, on hot days, the temperature is over 37 degrees C. Radiation, conduction, and convection all drive hot heat into the body instead of taking it out. So when you think about that, so that's Fahrenheit. If it's 103 out, you're going to get hot because the only mechanism left to keep your body from running a fever is evaporation. So you're going to be sweating. So after several weeks in the tropics, you find that you can produce 3.5 liters per hour. Sweat. Wow, that means you got to be drinking a lot of water. That's a lot. That's like drinking a quart of water every hour or something. So then you want to calculate the heat loss. So it's more or less the same calculation. Since you're going to get this, I'm not going to go through the whole calculation with you here. But you're just going to take this and you're going to multiply it by the heat loss, which is really 2.5 times 10 to the 6 joules per liter. It's the same as kilogram for water. And you're going to then be able to find that you get joules per hour, and then you're going to convert it to seconds, and you're going to find a metabolic rate of 2,430 watts. So that's pretty high metabolic, or not metabolic rate, a rate of heat loss. So the good news is you can go out and you can still work pretty hard outside, working in the yard or whatever you're doing. You got a way to get rid of a lot of heat if you're sweating that much. It's going to be gross. You're going to it's going to get you sick, but you're not going to essentially run a fever. Your body will be able to maintain your body temperature. Okay, let us see. We got two more. We got enough time. Let's go ahead and see if we can finish these. Giant redwood tree. It is 100 meters tall. Its trunk is 2 meters in diameter. It's made up of a bunch of pores, each 30 microns in diameter. Okay, the pores take up about 10% of the volume. So your tree trunk has a lot of these pores, but it's mainly on the outside. The inside sort of dead region, so it's not going to count as far as water flow. How many pores are present? Okay, so if you know the size of the pore and you know the size of the trunk, how many are present?
You get the volume of the tree times 10% and divided by each individual volume of the pore.
You could do that, although I would prefer to use cross-section area, because you're going to have to multiply by each one by 100 meters and they'll cancel out. So let us do first the cross-sectional area. So the number is going to be the total cross-sectional area of the tree. It's 2 meters in diameter, so it's pi times 1 squared. So it's pi meters in area. So I'll just write pi 1 squared. And you have each one is 30 microns in diameter. So it's pi times 15 times 10 to the minus 6 in radius squared. And then there's only 10% of the tree contains these pores. So you're going to get a 0.1. There's only 10% of them. So it's really, this area ought to be this divided by 10. And what we find is there's still going to be a lot of pores. The pi's will cancel. 1, that's 0.1 divided by 15 to the 6th squared. You're going to get, my calculator always have to count dots. 1, 2, 3, 4, 5, 6, 7, 8. 4.4 times 10 to the 8. Or about 4/10 of a billion of these little pores. This is the xylem that carries the water. Okay, if water is flowing up the tube at an average speed of 1 millimeter per second, what's the total volume flow going up the trunk? So, how would you get the total volume flow? Well, it's one of the equations you have to remember. A times V. So you can take the area, and the easiest thing I think is just take the numerator here. You have pi times 1 squared. That's the total cross-sectional area of the tree. And only a tenth of it carries the water. That's the area. And the speed is this average speed given, which is 1 millimeter per second. So 10 to the minus 3 meters per second. And when you do that calculation, you get pi times 0.1 times 1 e to the 3 negative. You're going to get 0.00031. That's basically the pi times meters cubed per second. So you have water going up the tree, and if you want to, you can write that in a little more intuitive units as 0.31 liters per second. So going up that tree is 1/3 of a liter per second, which is not a huge amount, but that's still a lot of water. This guy is climbing up that tree every second. You've got multiply by 60, and you'd have 20 liters in a minute. I mean, that's a lot of water. So, see, what pressure difference is needed between the top and bottom of the tree to drive this flow? Okay. That you're going to need to get an equation, which I did not tell you had to memorize, but I gave you in the problem. Flow is delta P over delta X, pi a to the 4th over 8 eta. So that's one of those equations where you don't have to know, you don't have to memorize it. In particular, you don't have to remember the pi and the 8, that kind of thing, but you do have to know how to use it. So we've calculated what the flow is. So really you solve this for delta P. Delta X is going to be your 100 meters. So delta P is going to be the pressure difference between the top and the bottom, which is what you're after. Eta is going to be your viscosity. Just use water. You might think sap's kind of sticky, but really sap's sticky after it comes out of the tree, and a lot of the water evaporates away and you get this sticky goo. But going up the tree, it's pretty much water. Pi A here you have to be a little careful with. This is really the flow through one of those little tubes. So you'd use your 30 microns, actually divided by 2, you use your 15 microns, but then to get the total flow, you have to multiply by the number of these that you calculated. So your flow in one tube is the flow total divided by the number of them. And you can solve that for delta P. And I'll just give you the bottom line here. When you calculate the pressure, you get something that is, if you convert it to atmospheres, 36 atmospheres. So that's a lot of pressure to go up. But that's a redwood tree, so it's a big tree. But it takes a lot of pressure to raise that water up the redwood tree. And it's a fascinating question on how that works. And we aren't going to go into it in detail, but it's basically capillary pressure up at the top in the leaves, which kind of pulls it up like a wick. But if you had the capillary pressure through the entire trunk, it would require you to have a much smaller radius, and you'd end up having much more viscous, and you can never do it. So water is actually hung in the tree through tension. So water you don't usually think of as supporting tension, but it can support some tension. So the water's capillary pressure up in the leaves and then hung in tension, which makes it kind of unstable, because if any bubble would form in the water, that bubble would just grow because the water is essentially a negative pressure. So the water in the tree is essentially in sort of a unstable, metastable state. Yeah.
And then when people are trying to tree sap, there's a spike in it, and it kind of maple syrup comes out of the tree because of the pressure difference.
Yeah, well, it's sort of like that. Although you'd expect that it would almost suck into the tree in some ways because the pressure is sort of huge. Well, it's a negative pressure down near the trunk. So what happens is sometimes little bubbles do form, but the sap, the xylem, has these tiny 30 micron diameter pores, but they're in little sections with little tiny channels between them. And if a bubble does form, it usually gets trapped and just kills one piece here and doesn't kill all of them. So that's why the tree is basically only alive out on its rim. The inside has had so much time go by that basically it's filled up with air, or it can't maintain that sap flow, and the sap is out on the rim going up in sort of this weird metastable state. So it's a fascinating story. You don't have, the question didn't ask for all that extra detail, but I just wanted to let you know it's the classic problem of the ascent of sap in trees is something that botanists worry a lot about. It's something physics has implications for. Okay, problem 7. Small protozoans fall sinking to the bottom of a lake through gravity. So it's sinking with mg. There's a force going up, which is given by Stokes' law, which is 6 pi a eta v. So it's proportional to v. So this is just like that problem we looked at in objects falling through air. We assume that it's proportional to v, and you can calculate then the terminal speed. And really, in this case, the terminal speed is just when the two forces are equal, so that it falls at a uniform velocity. And you can work that out, the density and whatnot. The thing that's kind of interesting about this problem is that this is an object this is a protozoan in water. If the protozoan had exactly the same density as water, buoyancy effects would not even make it sink at all. So I give you the density of the protozoan as 1010, whereas the density of water is 1000. So what it really means is this gravitational force is sort of down by a factor of 100 because gravity is the same, but the buoyant force bucks it, and you end up getting only 1/10 of the size of the force. So remember, when you have objects floating in water, buoyancy can play a role. And that's pretty much what the exam is. So last chance. Any questions that you want to ask before we go? Okay, in that case, if you have not handed in your homework, hand it in on the way out. If you haven't gotten homework 1 or 2, I have them with me. I will see you on